Okay, we're good. Yep.
All right, welcome to week 2 of programming. Yay! So like we mentioned, we will be recording this and posting it to YouTube later for you guys to reference later. We introduced ourselves last time, but just in case, I'm Risa.
Oh, okay, and I'm Jacob. Yeah. So let's go over the content from last week. So I talked to you guys about what it means to be a programmer. You're just writing programs, which in of itself is just giving your computer instructions that it will follow, kind of like an obedient dog who will listen to every command you give it. And this flowchart just kind of shows how your ideas and concepts as a programmer come to fruition in your hardware. So you as a programmer, you are programming in an integrated development environment, or IDE. It's just what programmers write their code in the same way that you write your essays in Google Docs or you create your presentations in Google Slides. It's the same thing with IDE. And you can see on the left, we have that Android Studio icon, which we will talk about in a little bit. And we're writing code for a program file. So this is what we're actually writing our code in and what the computer will interpret. And we write in a certain programming language, which in robotics we use Java, but there are plenty of other programming languages out there that we use for a specific purpose. And so this program file gets interpreted by our little computer, but it needs some help. It won't be able to read human code, so it needs the help of a compiler to turn that human code into machine code, ones and zeros, binary, and that computer will take in that input, that code, and produce an output on our robot and other interfaces. So our hardware controller will send electrical signals to our hardware, to move our motors and servos. So to break down a programming language, it's just like a regular language where there's vocabulary, grammar, and together makes up a sentence. So I'm just going to read the bullet points. In a programming language, you have a set of instructions that a computer can understand, and you have syntax rules that you must follow for that computer to be able to understand what you're coding, and you make a programming statement. And you don't just have one programming statement, but you have many statements. So you can see on the right, I made a little GIF, however you pronounce it, of just some commands that you might use in your robot, such as shooting, turning right, moving forward, and parking. And I wanted to expand upon this kind of analogy. Before, I only told you about the programming statement, but you can also make kind of like chapters or paragraphs with multiple programming statements. And then all those chapters kind of make up a whole book. So a program file is put together to put into a package, which is just a collection of those files, of those Java or Python or whatever files. And one question I do pose to you guys is, what do you call a collection of books? Maybe you can type it out or just speak it out. And there's a reason why I put this question, but what do you call a collection of books? Okay, if no one's going to answer in like the next 10 seconds, I can answer for you guys, but just keep, okay. Yes, a library. So go to the next slide. Yeah, you got it right. Oh, okay, go to the,
Oh, all right.
I put the slide on accident. Okay, yeah, go to the next one. So basically I made a little visual as to kind of how everything fits together. We have our vocabulary and grammar, our instructions and syntax, and together that makes a programming statement or your sentence. And you have all these statements and they make up like kind of a chapter or a paragraph. So your program file, and all those program files, all your Java files and whatever, they're put into a package. I would kind of think of it like a folder pretty much, and it's like a book. And you have all these books together and you put them together and you make a library. So a library itself, it's even bigger than just having one program for a robot. It's a collection of like code, documentation, pre-written programs and routines that you can reuse over and over again. So there are some teams that provide libraries for other teams to use, and I'm actually going to put kind of a link to the repository that I looked at, which is a library that another team has made, and I've tried experimenting with in the past. So it's just kind of like a template you can use, and it saves a lot of time having to write code manually. It just kind of wrote all the code for you. So if you know that you're using like, 4 motors for your base, you can just kind of find the program that kind of fits for that drivetrain. And because of libraries, teams are able to test their mechanisms much faster because they don't have to think about programming it because all the code is already out there. And yeah, go back to the previous slide because I put them backwards. So again, I kind of just broke down the statement into its 3 parts. We have our instruction, our syntax, and kind of the parameter. So instruction is vocabulary, the syntax is the grammar, and the parameter is kind of like the content of your sentence. I'm not really going to go too much more into this because I explained this last time, but that's all you really need to know about a statement. It's just instructions, syntax, and parameters. So let's go to the next slide. So I'm just going to read this off. Just like how there are many languages around the world, there are different programming languages that are designed for a specific purpose. So there's not just Java, there's Python, C++, C#. There's also like data querying stuff like SQL. So some programming languages are better for managing like numbers and whatnot. Some are better for like web design. So you got like HTML and all that. And just like how every language has different vocabulary and grammar, so there's a programming language with different instructions and syntax. And so now I'm going to pass this off to Risa, who will talk about the different programming languages.
So just as a reminder, we were initially planning on using Python, which is very beginner friendly and easy to read. And additionally, it doesn't have as many syntax rules. I went over the slide last time. So additionally, there's Java. It's the industry standard programming language generally. It's object-oriented. So essentially what that means is you can, I guess, assign characteristics of different files to new files. So like, we'll probably go over this a bit more in depth in a future lecture. But essentially, just you can think of it as a relationship in which, let's say that hypothetically we have a file called dog, and we give it all the characteristics of a dog, and then we make a new file called, I don't know, like Chihuahua. We can apply all of the characteristics of that dog object and say, oh, a Chihuahua is a dog. But yeah, we'll go more in depth into it at a later lecture. And then refresher from last time as well, IDEs or integrated development kits are the environment in which we write and edit our code. Specifically, Android Studio is the one that we use for robotics. So let's see. Jacob will go more in depth into how we upload code to our hubs later, and then he'll also go over what the hubs are. And commonly for Android Studio, you can use Java, C++, Python, HTML. It's very versatile. So programming in FTC, we went over the slide last time as well, but essentially you're trying to program for both the autonomous and the teleop periods during the game so that you can complete the assigned tasks that you need. So in autonomous, there isn't any user interaction at all. The robot has to run on pre-programmed instructions. So ahead of time, the robot already has an idea of where it needs to go. And then with control structures, the robot can adapt to the environment and move based on a specific condition. So essentially, for control structures, you know how in autonomous, the rings, when you start, there can either be no rings, I think 1 ring or 4 rings. Essentially, we can have instructions already set up in our code to say, oh, if there's no ring, I want you to run this branch of code. If there's 1 ring, I need you to run this branch of code. And likewise, if there are 4 rings, I need you to run this branch of code. And they all end up leading to the end of the program. For teleop, it's user controlled. So you're using a controller to actually drive around the robot. Yeah. So as you can see over here, we're actually able to map out what commands certain buttons actually do when we press them on the controller to run certain pieces of code. I went over this last time as well, but essentially teleop code will run in a loop and keep looping and checking for these conditions and running these corresponding commands until you press the stop button. And now onto the
new stuff. So there is definitely a lot of things to go over in this one. We're not really going to talk about too much code, but at the end we will get a little bit into like GitHub and other stuff. For this presentation, I want to focus on electrical and hardware. So for our robot to move, not only do we have to write programs for it, but we need to wire the hardware as well, the electrical. And electrical, we're concerned with the computer, the interfaces, the hardware controller, the hardware itself, and all the wiring in between. So a lot of these slides, we're going to learn about what each component does. And it's good to know what you're working with, because then you know what you can program. So you know what you can program. So next slide. So kind of before we go over everything, I do want to go into a little bit like chemistry, physics kind of stuff. So we have electricity that we're working with, right? So electricity just has to do with the flow of electrons between atoms in a conductor. So let's just kind of break that down. So everything is made of matter of these atoms. And in every atom, you have a nucleus, which inside of it, there's protons and neutrons. And then surrounding that nucleus is your electrons. So all those little gray dots you see right there are the electrons that are kind of orbiting around our nucleus or atom. And in short, atoms have spaces where electrons can flow. So you can see that there are like different rings around these atoms. And kind of the outermost ring is called the outermost valence shell. And that valence shell can only hold up to 8 electrons. But as you can see for the atoms of copper, so Cu, and gold, Au, you can see that there's actually only 1 electron in its valence shell, which means there are 7 electrons, 7 spaces where those electrons can kind of flow and like go around in. Unlike other atoms like oxygen and carbon, they're not so conductive because their valence shells are already filled up. You can see that oxygen has 6 atoms, or it's not 6 atoms, 6 electrons, and carbon has 4 electrons. So basically, electrons are repelled by a negative charge. You can see there's that one picture of like electron flow. They're trying to get away from that negative charge, and they are attracted to kind of a positive charge. And you can also see at the top, I put a picture of like a little circuit, and it kind of shows how electrons kind of flow. So again, you have that positive charge, and it gets kind of taken away from the electron, and the electron flows through the circuit. It lights up the LED, and then it comes back to bond with like the lithium ion. So basically, you don't really know, you need to know any of this, except for the fact there's positive and negative charge. That's what I want you to take away from this slide. So these flow of electrons performs the work in our hardware. It's what makes our motors move. It's what makes our computers compute. And that's pretty much it for this slide. So I do also want to go over pulse width modulation. So to control our hardware and send information, we send an electrical pulse that varies in width, aka pulse width modulation. So the thing with kind of electricity is that it can only really be on or off. There's either an electron or no electron. So instead of just counting like electrons, we have like this little pulse, and how long the pulse is kind of like the information or exactly how strong the voltage is going to be to our kind of motors and servos. So the important thing to understand, okay, so I pretty much explained that. The duration of the pulse changes the average voltage, and information can be taken from that, So that's it for that slide. So now we're kind of going to have to go over wires. So the electricity will have to flow through something. It's going to be our wiring, performing work and making our hardware move. So inside of these wires, our conductors are like copper, not really gold. That's more in like expensive things like our phones. They actually have a little bit of gold in them because they're really good at conducting electricity. And so anyways, they're color coded. So the red wires are positive charge and the black are kind of negative. And the thing about electricity is that it doesn't flow until there's a complete circuit. So if you're ever wondering why that wires in like bundles of 2, that's because there needs to be a way for electrons to flow in and then out to complete a circuit. And then we kind of have other colors like white, yellow, green, whatever. And they're just kind of like signal wires. So you'll see like in encoders, they have extra wires, and that's going to, pulse width modulation kind of stuff. And then, that's pretty much it for that slide. Electrons can flow in a complete circuit,
And then also, just as a side note, these particular adapters are known as Anderson power pole adapters. So they're really nice because you can literally just like plug and play instead of like having to deal with wiring. Oh wait, did you mention it? Oh,
no, I don't think so.
All right.
I don't know. I wasn't really paying attention. So there's also this thing called USB, which if you didn't know, stands for Universal Serial Bus. So engineers kind of came together and they kind of all agreed upon a universal standard for like data transfer and charging. So at the moment, USB-C is kind of the most common, most efficient kind of port out there. You'll see them in pretty much all the Android phones, on new iPads, pretty much everything. For some reason, iPhone is still using Lightning like port, and it's like really ugly, and I don't know why. I feel like they should just switch to USB-C, but I guess Apple just wants to make a monopoly on like chargers and whatever. But anyways, in robotics, we kind of use all these different cables, which I don't really want to go too much in depth, but that's just kind of different cables we use, and that's what they look like, Next slide. So now we're actually going to get into kind of the little interfaces. So for our inputs on our controller to do something on the robot, we use a driver station app on a phone as their interface. So we have these controllers that are connected to a phone, and this phone has this app, driver station, and it kind of shows a lot of information, such as kind of what network you're connected to, your ping. So if you have higher ping, your inputs are going to be more laggy, and the robot's not going to be responding as quick. You can also see kind of the battery, how much charge you have left, and the voltage as well. So you see that really big white button in the middle. That's how you start your autonomous IntelliHub, although it is currently running because it has a pause button. So right now it is running. And you can also see at the bottom, it shows kind of messages that you've coded in your program. It's going to display them at the bottom. And yeah, that's about it for that slide. So I do want to go over how exactly does a controller, which has a USB end connect to a phone, which kind of has I think a micro USB. I'm not sure what port that is, but in robotics, we use Logitech controllers in this competition, and to connect them to our phones, we use what's called a USB splitter, and they're also called like Lisa, what are they called? They're like OTG.
OTG, on-the-go cables.
Yeah, so you're able to connect, because in the competition you can have two drivers, which means you'll have two controllers. So you need this kind of USB splitter to connect both of your controllers to one output or one input, that little port at the end. And then you have a USB female to micro USB, which connects that little USB splitter to our phone itself. And from that, the controller is able to communicate its inputs to the phone. Next slide. And so now we have the other end. So there's actually two phones involved in this. You have one phone that's connected to your controllers, and then you have another phone that's connected to your interface, the hardware controller. So it receives information from the driver station through Wi-Fi direct and relays it to our hardware controller. That's pretty much what it is. You can connect your computer to this phone to upload code. Although you'll see in the next slide that you don't have to upload code to this phone. Instead, you can use what's called a control hub, but I'll explain that later. And you can also use this app to configure hardware devices. So you need to tell your program, your phones, hey, what motors, what servos you're using. And you don't have to use this app. You can also just use the driver station. But yeah, that's just kind of conventions, basically. All right, next slide. So here I made like a little visual. You can see that we have our controllers, which are connected to our driver station. And we have that little Wi-Fi icon. So the driver station and the robot controller are kind of communicating with each other. The driver station is telling robot controller inputs, and the robot controller is really relaying back information about like our robot, so the telemetry or messages at the bottom. So a robot controller itself is connected to our hub, the hardware controller, which itself is kind of the interface for our hardware itself. I won't explain it here, I'll explain on the next slide. So next slide. So now we're going to talk about our expansion hub. So it's basically just, it's the interface between our computer and the hardware. So between our phone and the motors and servos, it turns that information given by the phone into electrical pulses, or again, pulse width modulation, that it sends to the different ports it has. So you can see on that second picture at the bottom, that's like the little connection, the mini USB that connects to our little phone. And the different ports it has a port for kind of the source of like our electricity and whatever, that little yellow thing, the battery, yeah. And then we have ports for our motors, which are below that battery thing, so 0 through 3. So there's 4 ports that you can use, so up to 4 motors can connect to one hub. Then we have the ports for servos. There's 6 of them. I haven't really seen anyone use more than like 2 really, but yeah, there is up to 6 servos you can use. And you also kind of like have I/O ports, so basically meaning like input output. Our sensors will not only receive electrical pulses, but they'll be able to send them back to our expansion hub and kind of relay information that it's sensed. But we'll talk about that later. And yeah, that's about it for that slide. So now there is another hardware interface that we'll talk about. It's the control hub. So it's unique in that not only is it a hardware controller, but it has the brain of the computer itself, a CPU. So it's kind of like they put the phone and the expansion hub together and turned it into one thing. And it's really cool. You upload code to this instead of the phone. And Risa can vouch for this. It's definitely a lot faster to upload code to your control hub than, say, your phone. It also has a lot of, oh, sorry, you were going to say something?
No, I was just confirming.
Okay. And then it also has more like USB ports for connecting cameras. So you can see there's a USB 2.0 and a USB 3.0. Also, if you want to know the difference between 2.0 and 3.0, it's just that 3.0 just is a faster data transfer. I'm not sure exactly how much you can transfer per second, but there's that. 3.0 is better. I mean, higher number, right? And it also has USB-C. That's what you'll connect. What's you call it? The USB-C is for connecting that to your computer when you're uploading code. And a mini USB, say if you want to connect it to a phone, I guess. You also have an HDMI port. That's if you wanted to connect it to a webcam, which I'll talk about later. And a micro SD, which is just kind of extra storage that you might need for image recognition or just maybe some other code. And
Jacob, wait.
That's not right? What is it?
The HDMI port is
or
like
is it to display something?
It displays, so like, you know how in the robot controller there's the UI? If you like plug in a monitor to the HDMI, it just shows that, I think.
Oh, okay.
All right. Yeah, that's it.
All right, thanks for correcting me, Tyler. All right, so yeah, I was wrong and Tyler's right, so listen to her for that one. Okay, but it has everything else that the expansion hub that has the same amount of ports and everything, so yeah, next slide.
Oh, just like a side note, what's really nice about the Control Hub is that you don't have to worry about mounting a phone, which ends up saving space. So if you were to just use the Expansion Hub with a robot controller, you'd have to actually designate a place on the robot for your phone to go so that it doesn't like fall or disconnect or anything. So yeah. Okay, have fun.
Yeah. All right, so now we're going to talk about the motors and servos themselves. So these work by sending again, electrical pulses through its power pole connector. And like Risa said, did you talk about the power pole connector and how it's just plug and play?
Yeah.
Okay, so yeah, they're really convenient. It's very easy to work with. It's not fiddly with like other connections that we don't mention, but it can also work like a servo using, oh wait, sorry. So the speed, how fast the motor rotates is based on the current supplied by the hub. And it can also work like a servo using encoders, which I'll talk about a little bit later. So each motor has its own gearbox. I think Tyler's mentioned this before. So there's a gear ratio, and it's basically the difference between speed and torque. So if you have a small gear ratio, with a small gear ratio, it doesn't have a large reduction, so it's going to move faster. But if you have a large gear ratio, there's a larger reduction. That means that it's able to move like more heavier things, I guess. I didn't really explain that too, I'm sorry, but basically the smaller that gear ratio, that motor you see to the right is a 40-to-1 reduction. It's going to be slower than say a 20-to-1 gear ratio like NeverX. So it's used for just like general like fast movement. So you're going to use motors for your base, linear actuators, and then your intake outtake. So you saw like the flywheels and like the little rollers and whatnot that Tyler talked about earlier. So yeah. Next, we have our servos. They work by, again, just sending more electrical pulse via a 3-pin connector, and that's what they kind of look like. And again, keep in mind that this color coding kind of is universal, so that black and red, black is that negative charge, red is that positive charge, and then that white is kind of like the information, the pulses and whatnot. And so a typical servo has kind of 180 positions based on 180 degrees, but like Tyler said, there's also 90 degrees and 360 degree servos. And they can also be continuous and work like a motor, except they're very weak. And why would you use that? Anyways, you would use it for like precise slow movement, so like a pivot in arm or the swivel for that swivel drive base, and also for grabbing for like that claw grabbing thing that Tyler showed. So yeah. So with sensors, instead of sending electric pulses, sensors convert stimuli like heat, light, sound to electric pulses, which gets relayed to our interface, the hub, and the computer. And so these sensors can help us know when a certain stimuli is sensed, like detecting an object or getting to a certain position. So the first sensor we're going to talk about is the encoders. So encoders convert kind of motion to electric pulses. They count in ticks. So basically every time you do a full revolution of that motor shaft, it has a number of ticks. It's constant. So for NeverX motors, it's like 1440, I think. So how encoders work, okay, sorry. Anyways, so how encoders work, there's different kinds of encoders out there, but the one I'll talk about is with magnets and signals. So it kind of uses two magnets that rotate and kind of change the signal of a channel. So you can see that in our clockwise motor, when it's turned clockwise, there are two signals, and whatever is the leading signal, so A came before B, so channel A is leading before B. That means it knows it's counting clockwise. And then with counterclockwise, you can see that that's channel B signal comes first before the A, so it's knows it's turning counterclockwise. And so these encoders, what you'll find is that our motors in robotics actually have encoders built into them. But for some other motors, they don't have encoders and you have to add them separately. But for robotics, again, they're all built into motors, so you should probably use them. Well, you should use them. You'll see later kind of the applications for it. Next slide. So in our control hub, in our expansion hub, what we have is an inertial measurement unit, or IMU. And it's actually consisted of like multiple sensors. So one of the sensors it has is a 3-axis accelerometer. So when you think of acceleration, you usually think of kind of like increasing its speed, but actually acceleration just more has to do with the change of speed kind of over time or direction. So you're able to get information about that. Then you also have a 3-axis gyroscope, which you'll see is just kind of the rotation in the 3 axes, X, Y, and Z. They're called pitch, yaw, and roll. Yaw is particularly good. Like that's what we used to kind of figure out kind of direction we're going. Like we can use the gyroscope to tell the robot to go to a specific degree, basically. So if you want to turn 90 degrees, we would use the gyroscope and some clever code to do that. And we also have a 3-axis magnometer, which from my understanding is just orientation. So it kind of knows if it's like standing upright or it's on its side. Next, we'll talk about computer vision. So the phone, you know, it has a camera that we can use, or we can use an external camera connected to the control hub, and that, you know, we can use that for computer vision. So we take in those images and those videos from that camera, and using filters that amplify certain features and special algorithms, the computer processes these images and are able to identify certain objects and even track them in a live video feed. It's really cool. I actually tried this once, and Tony, you can vouch for this. I was at your house and we were trying out the computer vision, some code that I stole from another team, but it actually worked. It showed that it was able to recognize like the kind of the skystone blocks, if you remember that. That was really cool though. It's kind of hard to work it out. That's why I use another team's code. There's a lot of, it's very complicated and there's only so much that I know. So, but it's definitely really interesting. If anyone else wants to say anything about it, since you guys kind of did computer vision recently, Tyler?
Oh.
I don't know. Anything?
I feel like, yeah, that was our Tyler thing.
I mean, yeah, you could like kind of, with computer vision, you can kind of calculate your distance away from objects, and kind of like your robot will have an idea of its position in comparison to the object, so it could potentially automatically drive up to the object without driver control. Pretty cool. It's a lot of trig, some math, but yeah.
All right, we did that in FRC with like spacing out our robot from the power port. Yeah.
Mm-hmm. And you need to know the angle that you're looking, that your camera is looking at. Like, yeah.
Okay, but yeah, that's all we have for computer vision for now. Next, we have the color sensor. So it just kind of converts color to, again, pulses, but this time with a 4-pin connector, but it's just kind of the same idea, just sending signals to our hardware controller. So it returns values of red, green, blue. There's also alpha, from my understanding, is kind of like transparency, and hue, so basically how light or dark something is. And it ranges from 0 to 255, with 255 being the strongest sense. So if for red it reported 255, that means whatever we're looking at is super red. So there's this light you see. So on our robot last year for Patriotic, we used a color sensor to kind of identify the sky stone. Although it didn't really work out in the end, but it was really cool kind of working on it while I was in Tony's house. You can see that there's a really bright light. And so the reason why we have this bright light is so that whenever it's detecting colors, it has the same lighting conditions. Because what happens is that if you're detecting something in like a low light condition, it's going to report different results than if you were in like a bright light situation. So with this bright light, it's going to keep lighting conditions the same. And so it's always going to report kind of the same values. The other thing you need to understand is that unlike computer vision, where you can see things from far away, with a color sensor, you have to put it super up close to the element. So for like our autonomous, we had to drive up super close to the block to be able to kind of tell if it was like yellow or black. And that is kind of a problem with the color sensor. It's very limited in what you can do. And if you ever have the chance, I'd totally pick up like computer vision and all that. But that's all I have for color sensor. And so this is kind of a little demonstration of how sensors output like information to our driver station. Hopefully it's not too laggy. It's kind of hard to see, but you can see at the bottom there's like messages that are kind of displaying the distance between that of the sensor and the object. It's really hard to read, but yeah, it does change. It's pretty cool, and it is accurate to like the inch and whatever. And so that sensor in particular, it looks more like a ultrasonic sensor, I think. We don't go over distance sensors in robotics because we don't really use them, and they're not super great. I didn't make a slide on them, but that's what that sensor is. It's a distance sensor. Next slide. All right, so we have all this electricity flowing around, but we kind of need a source. So obviously there's a battery. We use a 12-volt battery with yet another power pole connector. And the one thing to note is that, again, the speed of the motor is dependent on kind of how much electricity is flowing through it. And voltage is kind of like the pressure of the electricity, I guess. I don't really know how to explain it. But basically, over time, as you use your battery, the voltage of your battery drops, and it won't be like 12 volts anymore. It'll be like 11 or 10. And in your code, you might tell your motor to go at its max speed. So you want to do like set power 1. And that means that the full amount of electricity will be sent to the motor. But what will happen is that if there's only 11 or 10 volts, it's actually going to go a little slower. Even though you told the code for that motor to go as fast as possible, it will be slower if it's a lower voltage, basically. So pretty much between matches, you should always like charge your battery and switch them out and keep them at like the highest voltage you can so that robots can move at their optimal like fastest speed. And well, we have to cut the circuit. We don't want that, for that battery to be running all the time. We got to turn that thing off, kind of like our phones. Basically, we keep them on. It drains the battery. If you turn off the phone, it's not draining the battery anymore. So we just kind of have a switch that breaks that circuit. And yeah, it's pretty self-explanatory. So to put everything together, I made this little kind of diagram thing in my in our engineering notebook for Patriotic last year. And this kind of stuff actually won me the control word. I did so much documentation for our code and everything, and this is the wiring. So you can kind of see on the left that I kind of explained what each little thing is, including like the physical device, the group, the hardware, and also all the little different arrows that are color-coded. So we can go through everything one by one. We first talked about our phones. So again, this is kind of like the computer. And this computer is connected to our little interface, the REV Expansion Hub. And it's going to relay these electrical pulses to each of the different hardware, the motors and servos. And you can also see on the second expansion hub that a color sensor is connected to it. So the color sensor will be sending electrical pulses back to the expansion hub and kind of give us, readings of how much red, green, and blue our little element has. And so it's actually going to connect back to like our robot controller and relay that information to our driver station. You can also see kind of on the left, we have our battery, which is connected to the expansion hub with a switch in the middle. And you can kind of see kind of the yellow, that's like, the connection for like where electricity should be like at, yeah. And there's also encoders I talked about earlier. They just kind of count motion and steps and ticks. And they're connected kind of to each of the motors because they have it built into them. And I think that's about it, really. Yeah, I think that's every little thing, but yeah, it's pretty cool. So now we want to go back to our little flow chart for autonomous, but this time now we know all the little like hardware and sensors and everything that goes into it. So first, we kind of start off our little program. So we have to press that big circle in that middle of the driver station. So now the program is going to start. And then the first process it's going to do, it's going to declare its variables. I'm going to tell it, hey, we're using these motors, these servos. Here's some sensors that we want to take readings from. And then we have this next kind of decision, wait for start, which kind of waits for the driver in the driver station to press that play button. And once that play button is pressed, it's going to the next process. So it's going to move, and it's going to have those parameters. It's going to move forward, and 1,000, so in milliseconds, is just 1 second. So it's going to move forward. That's just kind of an example process. That doesn't really mean too much, but the main thing I want to emphasize on is that next decision, which is count rings. So basically, we're going to use kind of our webcam as an example to kind of look at how many rings are on the ground. If there's 0, 1, or 4, I accidentally put 3, but there's 4. And after that, it's going to follow some processes like after it decided how many rings there are. And after that, it's going to go and end our autonomous. So it's just going to stop everything, and it's just going to kind of park there. Yeah. And then for here, it's kind of the same idea. We have to start our program using our driver station. It's going to kind of signal our robot controller that, hey, we need to start the program. Here's what motors and servos and sensors we have. And after that, like Risa said, we're going in a loop. We're always going to be checking if the driver station has pressed like the stop button, but if not, it's going to go through updating its sensors, so updating the readings on the driver station at the bottom, and it's going to go check through like each little input on the controller. Like if I move the left stick, that means I'm going to move a robot, stuff like that. It's pretty self-explanatory. And then once we press the stop button on our driver station, it's going to send a message to our robot controller to, hey, stop running the program, stop everything, and it's going to end. And so here's a little video that kind of incorporates all these different sensors together, and it's really cool. So awkward that it's quiet. I thought it would like play sound.
Is there sound?
I don't think so. Maybe it's just I'm not listening to the presentation. I'm only watching it. But yeah, that's kind of like an example autonomous that uses different sensors. They definitely use encoders, kind of tell like an exact distance that these motors will move, but it will also use kind of like what's called PID controllers, which is some calculus thing to be able to tell the robot to like optimize its movements basically. So you notice that it doesn't just move like forward and then back and then turn like left 90 degrees. It moves super smoothly because that PID controller is able to kind of calculate like the exact electrical pulses that we need to send to our motors and everything. They also use a camera. You'll see that at the very beginning. Can you play the video again? We first have to collect our sky stones, the ones with the pictures on them. And you can see there's a camera right there. So at the very beginning of that autonomous, one of the processes was like, go check the camera, see what position the sky stones are in. And after that, it's going to run like 1 or 3 programs to get that sky stone first. And then after that, it uses the extra time to get the other sky stones. And I wonder if it's adaptive, like it gets the blocks by looking at the camera even more, or it just always pushes the blocks in the same way every time. I'm not sure. But yeah, it's really cool that it's able to kind of get the rest of the blocks even though they've been knocked over. It's really cool. I'm not really sure the sensors are part of that, but yeah. So what's different this season? So while we can't work on the robots themselves, programming is actually not really affected. Without the robot, you can still program as long as you have a Chromebook with you. You can program each of the different subsystems. So I created like tests for each of the little things that are, okay, so basically a subsystem is just one part of the robot. So you know that in your robot, you have kind of the drive train. You also have your intake and outtake. In a robot, we kind of had a lifting mechanism, and we also had a pivot mechanism for PR's robot. So you can still program for all those different things so that when you get to school, you can test them right away instead of having to just write them. You know, it's just better to have everything already done by then. And you can also still kind of program a teleop if you understand what you're doing. It's just that you won't be able to kind of test them really, but if you know what you're doing, you're able to write everything beforehand without having to actually try it on the robot. And so, oh, I think this is on you actually. So I'm gonna pass this off to Risa for pretty much the rest of these slides.
Okay, so we emphasized last time that we can't be at school, and so if we're going to be able to do any programming, we're going to have to be able to do it at home. And it's also more likely that there are multiple programmers on your team. So it becomes a question of, okay, well, how do we share our code and collaborate on it so that everybody is on the same page and is coding on the same like updated files? So that's where communication and having the right resources and tools is going to be really, really important. So we have GitHub. We love GitHub. GitHub's great. So essentially, the easiest way to think of GitHub is Google Drive, but for code. So it's a software development platform that allows you to manage different updated versions of code using Git, which is essentially just a system that computers use to track changes in code. But GitHub's great because we're able to look at previous versions of our code and revert them back to an older version if we mess up a more recent version of our code, and great for sharing and synchronizing code instead of like having to manually copy and paste things into a Google Doc at PR 2 years ago. Jacob can vouch, but like,
Yeah.
It's really gross when you're trying to. Did you want to go?
No. I don't really have any comment about that. That's pretty much all I was going to say about this anyway.
Yeah, okay.
Yeah.
So this video does a great job of like explaining. Oh, actually, is there no sound?
Yeah.
Okay, we're gonna pull a pro gamer move.
Are you just going to like turn up the volume really loud so it picks up on your mic?
Oh, you know, that would have been smart.
Yeah.
But no, I would just casually switch to my laptop. Because theoretically, this will work.
Spoilers.
Okay, what is GitHub? Well, GitHub is a
Yeah, we can hear
platform
it.
that helps people solve problems by building software together. So, how does it work? This is Sam. Sam works on tractors all day, but not in the way you might be thinking. She builds the software that helps make tractors more efficient. And she does this on GitHub with the help of her team, BJ, Melinda, and Mike. Now, even though they all work on the same project, Sam and her team don't all work in the same part of the world. This is Eddie. Eddie also works on tractors all day, except he actually works on the tractors all day. And this is the Harvester L700. It's the latest flagship in the company's fleet of tractors. It's full of sensors and processors that produce a ton of diagnostic data. Eddie has a great idea for how farmers might share their data and improve their harvests. So Eddie opens an issue on GitHub. Issues are discussion threads where people can report bugs, request features, or even just ask questions. Sam is the first one on her team to see Eddie's issue, and she thinks that VJ would be the best person to start the job. And here's where we get into the nuts and bolts. Eddie isn't the only person using the Harvester L700. All over the world, other tractors are collecting moisture data, and they need to keep running smoothly even while VJ is working on the new features. He needs a dedicated place to experiment, so none of his changes end up on the farm before they're ready. So he creates a branch of the code, an alternate timeline where he can safely make changes to the software. Now he's ready to start writing a new feature. GitHub tracks VJ's changes and saves snapshots of his progress. When he's ready to collaborate on the changes with his team, he opens a pull request on GitHub. Pull requests let you show others the changes you're proposing so they can review and discuss them. This means VJ's teammates can help with roadblocks and even make improvements. On GitHub, everyone has a copy of the project. So if Melinda has an idea for something that will help make VJ's work even better, she can add it to the branch herself. GitHub keeps a record of everyone's contributions and feedback in the pull request, alongside relevant messages from the team's other systems. Once the team has signed off on the changes, VJ can incorporate the new code into the project. The new feature will be available to everyone as soon as he merges it in. Now farmers everywhere can all benefit from Eddie's great idea. But this is really only the beginning of the story. Because GitHub is the largest community of developers in the world, with millions of people sharing their projects, Eddie's idea could end up helping people in unimaginable ways. What kinds of problems are you trying to solve? Whether you're an engineer, a code enthusiast, or even a farmer trying to harvest grain, software touches every corner of our lives. GitHub is where people build that software. It's how they build software. Together.
Ooh, okay. And okay, are we back on the slides? We are. Okay. So yeah, GitHub's great for collaboration. So I invite any programmers that don't have a GitHub account to make one, and I'm going to be going through the steps. But like beforehand, so this is just like a watered down visual of what GitHub allows you guys to do as programmers. So essentially, Laser, you write the code, and then you can push the code to the cloud or GitHub, and your teammates are able to pull that code, make edits, push it back to the cloud where you can then pull it. So it's very convenient, and it's great for synchronizing code. Yeah, all right. So for anybody that's following along, if I go too fast, feel free to unmute your mic and just like tell me to chill and slow down. But start by going to www.github.com. And when you first open the screen, this box, I guess, for signing up should be on your right. And just go ahead and make a username and email that isn't your school email, because if it's your school email, you won't be able to access it after you graduate. So please use a personal email so that you can still come back to this in the future. And then once you have that set up, you can click the sign in for GitHub button.
So I guess when you're like done with setting it up, you can kind of like leave a message that, hey, move on to the next step. Because
I appreciate.
Yeah, because it takes some time for people to get there, but I guess we can wait on this slide. Yeah, just like leave in the chat, hey, I made it to this step. I've made the account, and we can move on. I also just want to see how many people are actually signing up, pretty much. Let's see. Now, for most people who already have like GitHub as an account, don't worry. We also have like another setup thing that I don't think as many people have.
Yeah, no, I just found out about the second part this morning.
Oh my God. It's a good tool though.
It is.
Wait, am I going to talk about it or are you still going to talk about it? I don't remember.
I can still go over it. I made the slides
Okay.
for it. So. Is it safe? Is it safe to move on? Any objections? Okay. All right. So the second part is choosing a plan. So make sure that you choose an individual plan, because this is just going to be your personal account, and a free account, because $7 a month is a lot. We're poor.
I was going to say something. So especially if you're starting out, you won't be able to like kind of use all the features of Pro because you only know so much. You wouldn't be able to take advantage of the Pro plan anyway. So yeah.
And then the next screen, I didn't get the chance to take a screenshot of it, but it's titled "Welcome to GitHub." It's essentially like a big like survey of like, oh, getting to know you stuff. You can skip it if you want just by scrolling to the bottom. Actually, since we're just posting this later, okay, wait. Option A, I just eat through these slides and then they can rewatch it later.
Right.
Option B.
Because I don't see anyone who has like left a message that, hey, I'm actually doing this, but it's, yeah. All right.
Is that all right with everybody if we just like go through the steps, and then for those of you that are rookie programmers and want to make an account, you can reference this later on YouTube. Thank you, Ruben. I appreciate. Okay. So after that, oh, okay.
Adam said something. I'm doing it, but it's pretty self-explanatory. Yeah, it kind of is, but for people who may be confused, this is just a clear like way of understanding how it, how to sign up pretty much.
Oh yeah. So after you set up your account, you're going to get a verification email from GitHub. So be sure to check your email, verify the address, and then you'll automatically be redirected to creating a new repository. For now, just ignore the page and click on the GitHub logo in the top left corner. We'll probably go over repositories in like a later lecture when we're actually able to like set up code and program with Android Studio. So congratulations, after you've done those steps, you finally made a GitHub account. But this is a feature that we were talking about that I just realized is available to students, GitHub Pro. So GitHub's really nice. They provide all the pro features for students that are still starting out. So it's completely free. You get access to a bunch of additional features, and it's good to take advantage of it, because free. So essentially, afterwards, you end up in your dashboard. You just click on your icon, go to settings, and then in settings to the left, there's an email tab. Make sure that you add your school account email. And then from there, you end up getting another verification email from GitHub. So make sure that you verify your email address. Don't panic if it takes a while for the email to come up, because when I was setting mine up today, it took a few minutes before I ended up getting the email for it. After you click the button, you'll be redirected to GitHub, and it'll say your email was either verified or there was an error trying to add the account. If there's an error, just try to resend the invitation link again. From there, you're going to Google GitHub Pro for Students and just click on the first link. It should take you to a page that looks something like this with GitHub Student Developer Pack on it. When you get there, click the Get Your Pack button. And essentially, since your school email should already have been added, select your school email. For Heritage, I guess it automatically recognized that it was a Heritage email. And then for the how do you plan to use GitHub text box, you can just like put for robotics. But yeah. And then from there, you get a thanks for submitting page. It says that it'll take a month max for a confirmation. So just like keep your eye out for an email on that. So here we have Tyla's GitHub account. Here you can see that she has a pro status because she's a pro gamer like that. But yeah. So I don't know if I ended up mentioning it earlier, but just like collectively, Jacob and I are considering, instead of teaching you guys Python, to just jump straight into Java, just because of like the hiccups that might come up with trying to teach you one language for a semester and then trying to transfer over to a completely new language after. So that's where Repl comes into place. So Repl.it is a web-based IDE, just like how VexVR was, where you can program directly inside a web browser. REPL stands for Read, Evaluate, and Print Loop. And like we said, it is a web-based IDE, so you can access it with your Chromebook. And it also has a multiplayer feature. I don't know. We'll probably will, huh? Will
What?
it just multiplayer?
Yeah. I have the kind of everything pretty much set up. I'm just waiting on you to.
Okay.
Yeah.
So once you have,
What?
making a Repl account would have been reliant on having your GitHub account set up.
Right, but you can also use your Google account and then later on link your GitHub account. Don't worry about it. You could use GitHub, but you know.
Okay, that's fair. So you can sign up with Google, GitHub, or Facebook. Again, don't use your school email because you want to be able to access this even after you graduate. This is the last slide. Is it? Oh.
Is it?
No, it's not.
It's not.
Computer, please, thank you. Okay. So this is just more for future reference, but when you want to make a new REPL, you click on the plus button at the top right corner, and then you select your language, give it a name, and then create your REPL, and yeah. You can also import repositories from GitHub. So if you have code on GitHub that you want to be able to edit on REPL, you can just import it directly once you have your GitHub account linked. So let's try out the multiplayer feature.
Yep, and that's where I come back in. So for anyone who's set up their REPL account, I'm going to be putting a link in the chat where if you click in the link, you'll be invited to a little REPL, so program file. And the really cool thing about this multiplayer feature, it works pretty much in the same way as being able to collaborate in Google Docs. Multiple people can be on the same REPL at the same time, and what you make changes to the program, what file you make changes to, it also updates on their end as well. It's really cool. So you can kind of collaborate together on like simple things like printing out statements, which I want to do right now. So if I can just get the link. Okay. So if you click on that link, and it's going to ask you to kind of sign it into REPL, and then you'll join that little REPL file thing. And from there, I'll kind of explain what to do, and then kind of just play around with the whole idea of multiplayer. I do understand it might take some time, so maybe we can wait for a little bit. But you can also see on Reese's screen that she's loading our little REPL. I'll give it like maybe a minute or two, and then I'll kind of explain more of what's going on. So kind of this exercise is just to pretty much just write your first line of code.
Yes,
but you can also see, you can see everyone else's code at the same time. So look, I'm going to make some...
Oh wait, if you're not interested in programming, no, you don't have to. You can if you just want to like take a look and like mess with it, but
oh, whoops. But yeah, you can see I'm like putting whatever. Oh, okay.
Oh.
But yeah. Oh, I see someone. Who's that? I actually don't know who that person is.
Oh, it's me.
Okay, wait, no. I mean, like, okay, I see Rice Angel, which is Risa, and then Thai-Asian, which is pretty self-explanatory, and then I Conquer.
Oh, I think that's Shane.
Oh, okay, that's cool.
I think.
Wait, hold it up. Bruh, it went away. Okay.
Oh.
RIP.
RIP.
Alright, it's fine.
Oh, I see you, Sophie. Yep. So it's really cool. You can already kind of start messing around with the kind of our main.java file. You know. So kind of one of the first things you'll learn when you're programming is if you put 2 slashes, Sophie, it makes what's called a comment. And anything to the right of these 2 slashes, you can type whatever. And again, it's really self-explanatory. It's just a comment. And it won't do anything when you actually run the code. It's just kind of there for you.
Yes, Sophie, we stand.
I want to wait on Adam because I know he was signing up for GitHub, so he's probably doing this as well. Let's see. I want at least like a few more people before kind of explain. Well, it's pretty self-explanatory. So I just left a comment right here. So pretty much you have this little instruction right here, and you can copy it or you can type it out on its own. And what I'm basically asking you guys to do is to type out this instruction. Oh, what the
Oh,
heck?
hello. Okay.
Oh,
hold
we were
on.
typing at the same time.
Yeah. Okay.
Okay, so here, let me just put this, yeah, Jacob, okay. So I'm just gonna delete this right now. So again, remember that our statement consists of like our instruction. So this instruction is a bit longer, but it's actually not so hard to understand. You can see that we're kind of referring to our little system, so the terminal, and then we're outputting something, so that's why there's out, and then print is just, you know, printing something on the screen, like our text. And ln is just meaning like new line. So every time you run the statement, it's going to kind of press enter. Yeah. And then inside, you can do quotations. That's how you start kind of a string, the little content of your statement. You know, just write my name and what my favorite food is. I never really thought about this, really. I need to think about it. But yeah, so if you're still on here, you can start writing your own little statement. So kind of right after recess, you can kind of just press enter, enter, and then kind of copy what we've written down. What is my favorite food? I'm thinking about it. It's kind of hard because I have like.
Bruh, just say something.
I can put anything, I know, but I'm actually taking this serious, okay? I'm a tryhard. I'm a nerd, okay? I have to be right about. Oh, I think someone else joined. Who? It's +1, so I don't know who just joined, but it looked like someone just joined. Oh, Emmanuel. Okay, cool. So yeah, you can also kind of add your own system.out.print. Yeah, obviously. I don't even think I spelled it. Okay, whatever.
No, that's right.
It's right. Okay.
Yeah.
I was expecting some Asian dish or something, but okay, go off.
Nah. I just gave up. I just gave up. Okay, so Adam, you see that I put like a little link right there. If you click on it, you'll be invited to this little REPL, kind of like a Google Doc, but code, right? So if you click on it, you'll be invited. You'll be asked to probably sign in or something. And then after that, you can kind of type in whatever. In this case, I just wanted you to kind of try writing out like kind of your first line of code. And also another thing is that you have to write these statements inside what's called the main class. That's one thing I forgot to specify. Because the thing with Java is that you have to start off with a main class, and then you write your code inside of there first. In Python, you don't really have any starting code. You can kind of just start writing statements already. But the way that Java is structured, you have to write your code inside of here. Yeah. So I'm gonna wait for like maybe one more person to write their like line of code, and then I'll show you kind of how to like run the code pretty much. Which, I mean, I already have it on there. Actually, we can try right now. Okay, so
Oh wait, you're not
Control
sharing your
Enter.
screen. Okay, Control Enter.
Yeah. Someone else do it. Oh, there's one error. Oh, that's on me. I'm a terrible programmer.
Yeah.
Would you look at that? I'm still living in Python. Anyways, now try it again. So you can kind of see that one person runs the code and it will actually update on everyone else's end. It's really cool. And there you go. It's printed on our little terminal, kind of the names and like food and whatever.
So as I mentioned before, you are able to import from GitHub. So Jacob and I are going to be experimenting to see if we might actually be able to use Repl to program for FTC, at least to have everything written down. We won't be able to like test anything per se, but this might be an option.
And I would say it has some of its own benefits, like the whole multiplayer thing. You know, programmers could be working on the same like thing at the same time, unlike GitHub. But I mean, GitHub kind of streamlines the whole being able to synchronize everything. But it's a lot simpler with Repl. Like everything is, you can see all the changes being made live. It's really cool. But once we get to Android Studio, we'll have to use GitHub for kind of synchronizing everything. I'm still wondering whoever like iConquer is, where that person went. Oh, there's Adam. Yeah. So again, because of the way Java is structured, you have to write your statements inside of these like little brackets right here. So you'll have to go past like Sophie's statement and then write your line of code there.
Alternatively, you could use line 6 or 7.
Yeah. Right, so you're writing down the instruction first, system, so kind of the actual like inner hardware, whatever, and then out our terminal, and then printing out what we want to print out to our terminal thing. And then once you're done with that, what you could do is you can, on your computer, hit Control Enter, and it's going to do on everyone's ends, kind of run the code. Yes, one thing to note is the semicolon, which I totally forgot. It's kind of like the period. It's kind of how you usually end statements. Python, it's different. You don't need a semicolon. I forgot that we're running in Java, so I didn't put the semicolon. But yeah, it's kind of a way to just end off your sentences. And there you go. Now it's updated. Now you have Adam, just Apple. Wow, that's so funny. Okay. Oh my God. Okay. I'm not sure if I'm really gonna go through too much else. I mean, you did write your first line of code. I could go over variables and other things, but I feel like that's more of a lecture for next time. I really just want you guys to kind of explore this whole IDE and just writing your first line of code. That's really what I want to accomplish here. Yeah.
So are we good then?
I honestly don't really have too much else. Plus, it's almost 3, so I think it's a good way to kind of wrap everything up. Yeah.
All right.
So if anyone wants to interject and want to like, join the Repl like last second, oh no, I'm still setting up my account. Say it now. Otherwise, I guess we're wrapping it up now.
Looks like everybody's good.
Okay.
Yeah.